I'm Shalini, we working as assistant professor of physics. In this video, I will discuss the topic for the session 23 for the first semester BSc of the chapter rigid bodies. The topic of this session is rotational motion about an axis and the concept of moment of inertia. Then before going to deal with the rotational motion, we have to know what is a rigid body, then what is motion of a body, translatory motion, and also the equations of motion in case of a translatory motion. Then what is a rigid body first? So a rigid body, it is nothing but it consists of a large number of particles, and all the particles over it occupy their fixed positions. And when a system of forces act on a body, the positions of these particles, they do not change, and the body as a whole, it is undisturbed, and the rigid body does not undergo any change in the shape or size by the application of the external forces. So these are the figures which represent the rigid bodies. So this is a rigid body having an irregular shape. These are the rigid bodies having a regular shapes. Then when we call the body is said to be in motion. So whenever there is a displacement in the positions of the body, then we say that the body is in motion. And that motion of the body may be a translatory motion or a rotatory motion. So what is a translatory motion of a body? So if all the points of a moving body move uniformly in the same line or a direction, the body is said to be in a translatory motion. So if the body is in a translatory motion, we define the terms linear displacement represented by the letter S, then linear velocity, linear acceleration, and also if some amount of force is applied on the body, F is equal to ma. Then what is a rotational motion? A body is said to have a rotational motion if a certain line of points during the motion of the body, if it remains fixed, then such a motion is called as a rotational motion. A pure rotational motion is one if a line of points during the rotation of the body remain fixed, and that line of points which remain fixed during the rotational motion of the body is called as a axis of rotation. So during the motion of the body may either move in any direction, that means it may have a translatory motion, or it may turn around and rotate in two or three dimensions, that means it may have the rotational motion. So whenever the body is in motion, it may have a translatory motion or a rotatory motion. Then if the body is having a rotatory motion, few terms we have to know. So that is, what is the first? Angular displacement. So what is an angular displacement? Means angle through which the line of points displaced in a given interval of time is called as an angular displacement. We denote that one by theta. So, and it is taken as positive for the anti-clockwise rotation and negative for the clockwise rotation, and it is measured in radian. Then the angular velocity. So rate of change of angular displacement is called as angular velocity. Angular velocity is denoted by omega. Omega is equal to theta by t. It is measured in radian per second. Suppose if the body takes one complete rotation, then the angle displaced in a given interval of time, capital T, it is nothing but equal to 2 pi. So angle displaced when a body completes one rotation is equal to 2 pi. So total time taken is nothing but equal to time period. Time taken to complete one rotation, we represent that one by capital T, that is the time period. Hence, the angular velocity is nothing but equal to, so angle displaced in one complete rotation is 2 pi, that is theta is equal to 2 pi, and time taken is nothing but the time period, so omega is equal to 2 pi by t. But we know that the time period is equal to reciprocal of the frequency of rotation of the body. So hence omega is equal to 1 by t is nothing but f. So omega is equal to 2 pi f. So this is the angular velocity. So then what is angular acceleration? So rate of change of angular velocity is called as angular acceleration. So it is denoted by alpha. So alpha is equal to d omega by dt, and it is measured in radian per second square. Then the relation between linear velocity v and the angular velocity omega. So let us consider a body which is having a rotatory motion. Let the body, that is the body, displaces an angle theta in time t seconds. Then from figure, the arc length, that is PQ, which we call it as a linear displacement, yes, it is equal to r into theta. Arc length S is equal to r into theta. Now divide on both sides by t. Then S by t is equal to r into theta by t. But we know that S by t is nothing but the rate of change of linear displacement, so which is nothing but equal to linear velocity, and rate of change of angular displacement is angular velocity. Knowing that one, if we substitute S by t as v and theta by t as omega, so we get v is equal to r omega. So this is the relation connecting linear velocity and angular velocity. That is v is equal to r omega is the relation between linear velocity and angular velocity. Then the relation between linear acceleration a and the angular acceleration alpha. So from the previous slide, we know that the relation connecting the linear velocity and angular velocity is v is equal to r omega. So here also again divide on both sides by t. What we will get? V by t is equal to r into omega by t. But the rate of change of linear velocity is acceleration a, and rate of change of angular velocity is angular acceleration alpha. Therefore, we get a is equal to r alpha. So this is the relation connecting the linear acceleration and angular acceleration alpha. So then we shall write the equations for angular motion. Knowing the equations of motion in case of a linear motion, so we will write the equations for angular motion. So first equation in case of a linear motion is v is equal to u plus at. Second is s is equal to ut plus half at square. And third equation is v square is equal to u square plus 2as. So these are the equations of linear motion. Now we shall write the same equation for an angular motion. For writing that one, just what we have to do is, so this is v is nothing but the final velocity. So and u is the initial velocity and a is angular linear acceleration. So angular velocity we denoted that one by omega. For final angular velocity, let us consider that it as omega 2 and initial velocity as omega 1. Just what we have to do is to write the equations for angular motion, replace the displacement, linear displacement s by theta, initial velocity by omega 1, final velocity by omega 2, and the displacement s as theta and linear acceleration a by alpha. If you replace those things, what we will get is equations for angular motion. As first one is omega 2 is equal to omega 1 plus alpha t, that is v is equal to omega 2, v u is equal to omega 1, and a we replace that one by alpha. So omega 2 is equal to omega 1 plus alpha t is the equation for angular motion, first equation for angular motion. Similarly, if we write the second equation, that is s is equal to ut plus half at square, yes, instead of s, we write that one as theta is equal to u as omega t plus half into a instead of a alpha t square. So et is equal to omega t plus half alpha t square, the second equation for angular motion. Similarly, third equation is replace this one by the particular terms. So omega 2 square is equal to omega 1 square plus 2 alpha t. So these are the equations for angular motion. Then what is moment of inertia? So according to Newton's first law, the statement for Newton's first law is every body continues to be in a state of rest or motion unless and until an external force acts on it. So it preserves to be in either a state of rest or motion unless it is acted upon by external force. So that means it will be in a state of, the body will be in a state of inertia unless it is acted upon by an external force. That means to overcome the state of inertia, certain amount of force is to be applied. And in case of a linear motion, the mass is a measure of inertia. Similarly, all the rotating bodies will also have an inertia. That rotational inertia of the body is called as moment of inertia. That means when a rigid body rotates about an axis, it has the tendency to oppose the change in its state of rest or of uniform motion about an axis. This rotational inertia of the body is called as moment of inertia of the body about that particular axis. Suppose if m is the mass of the particle and it is that particle is rotating about any given axis, then the moment of inertia of that particular particle is given by I is equal to mr square, where r is the distance of the particle from the axis of rotation. So thus, if m is the mass of the particle which is rotating about a particular axis which is at a distance of r from the axis of rotation, then moment of inertia is defined as the product of the mass and the square of the distance of the particle from the axis of rotation. Knowing this one, next let us calculate the total moment of inertia of the entire body. So for that one, consider a rigid body. Here this is a rigid body which is rotating about this axis of rotation. Then let this whole rigid body consist of a large number of particles. In that one, first consider one of the particle in it. Let the particle, first particle be having a mass m1 which is situated here, which is at a distance of r1 from the axis of rotation. Then moment of inertia of this particle can be written as I1 is equal to m1 r1 square. So this is the moment of inertia of the first particle. Similarly, consider a second particle having a mass m2 which is at a distance of r2 from the axis of rotation. Then its moment of inertia can be written as equal to I2 is equal to m2 r2 square. Similarly, there will be a large number of particles. If we write the moment of inertia for all the particles, what we will get is, suppose if we consider the third particle, I3 is equal to m3 r3 square, I4 is equal to m4 r4 square, like that, etc. Then the total moment of inertia of the entire body is nothing but equal to sum of the moment of inertia of the individual particles. So therefore, what you will get is moment of inertia of the whole body, it is equal to sum of the moment of inertia of all the particles, which is equal to m1 r1 square plus m2 r2 square plus etc plus mi ri square. This can be written as equal to sigma mi ri square. This is equal to, if we calculate the total mass of the all the particles, which is equal to the entire mass of the body, hence sigma mi, we replace that one by capital M and sigma ri by k. So hence moment of inertia, general expression for moment of inertia for a body having a mass m is equal to m into k square. So in this equation, m is nothing but equal to sigma mi, which is called as the total mass of the body, and that total mass is assumed to be concentrated at a point called as the center of mass, and in this equation, k is called as the radius of gyration. So this is the general expression for moment of inertia, that is I is equal to mk square. The SI unit of moment of inertia is kg meter square. Since mass is measured in kg and this k is nothing but the distance, so SI unit of moment of inertia is kg meter square. So this is about the moment of inertia. And I refer the books Properties of Matter by D.S. Mathur, Unified Physics Volume 1 by Dr. S.L. Gupta and Sanjeev Gupta, and Mechanics by D.S. Mathur. Thank you.